Back from the break. There was some confusion in the schedule where we were very honored that Jan LeCun had agreed to grace our workshop with a talk. And then there was some confusion because it seemed like some emergency had come up at the last minute and he wasn't going to be able to make it. But your workshop organizers have worked very hard, and we're very pleased to announce that we have salvaged the situation. And without further ado, I introduce to you Jan LeCun.
Good morning. Thank you very much, Tom, for this invitation. It is really an honor for me to be talking about deep learning for creativity and design. I mean, machine learning, but there is not much else, actually, to be honest, to be true. So I don't think I need to introduce myself. Everybody at this point knows me. Do you hear me, by the way? Yeah? Oh, now you hear me better. Okay, thank you. So yeah, it is my honor to actually do something to present all the posters that have been submitted to this workshop. And yes.
Okay, hold on. You're not Jan LeCun. What are you doing here? I am the real Jan LeCun. I am very happy to be here. Thank you very much to the organizers. Of course, I'm Jan LeCun, a chief AI scientist at Facebook, a data scientist at NYU.
Oh, I'm sorry, I am the silver professor of computer science at NYU.
I am a one-time Turing Award winner, potential...
I am the true inventor of convolutional neural networks.
I was the one that made the convolutional neural network in 1960 and 61.
I am the only person who actually knows how to pronounce my name.
In fact, it is pronounced Jan LeCun. Very tight. Jan LeCun.
I'm sorry, you're not Jan LeCun.
You are not Jan LeCun.
You're not Jan LeCun.
You're not Jan LeCun. You are a fake Jan. You are a deep fake Jan LeCun.
What?
You are not Jan LeCun.
Corey.
Yes.
Is it you?
Yes. Is it you?
It's me. Okay. Well, this is the real Jan LeCun. That's how he looks like. And he, yeah.
These are two photos of him so you can identify him.
Yes, and we have them also on our faces. He has lots of friends.
This was him last night talking over the posters for the creativity workshop with two of his friends. He aged majorly in one night.
Yes, yeah, it's fame and celebrity. And it's very funny. Look, he's smiling on one picture and not on the other, but let's not make things up like journalists do, because that's what journalists are.
Yeah, we don't want to weigh the story in on that. No.
So, yeah. It's a talk about convolutional neural networks.
Yes, we're very happy to be here at the Convolutional Neural Network workshop. There's 31 accepted posters.
Yes.
You can follow along at NeurIPS 2019 convolution.github.io.
Yes, it's listed over, and I think we should just start presenting them one after the other.
Yes, of course.
So yeah, that's the first one.
Very good. Visual indeterminacy in generative neural art.
Yes, that's very fuzzy and confused, and I think an actual Jan LeCun, another Jan LeCun has just said each hypothesis we assume will be knocked out by a contradiction elsewhere. So that's what's written in the paper. That's great, right?
This is fantastic.
And so that means that even Ernst Gombrich is predicting the common revolution.
Even Ernst Gombrich.
I mean, there are lots of artists in the room, right?
Yes.
Yes, so people know the joke.
Just by show of hands, everyone knows Ernst Gombrich, right? All right, okay, all right.
That's joke number one. Okay, so, look at who's that?
Very good. Jan LeCun weighed in on this, said, if you enjoy indeterminacy, you should try reading CVPR reviews of my ConvNet papers from the early 2000s.
Oh, we got hacked.
Hashtag torch, hashtag feel to learn.
Okay, we need to go.
Yeah.
We need to go on. So this one, do you have something?
Yes, unsupervised doodling and painting with improved spiral. Oh. This is great. Lots of very good blurry faces, images. Some of these look familiar, some of them less familiar. Lots of cubism, artistic.
Yeah, I think it's like a commentary on a meta commentary on abstract art. Like you need to minimize the amount of energy to create something abstract. Which is like something, yeah, anyway. I don't want to start a war.
Jan LeCun says, as a child in France, I learned about the deep connection between the lack of supervision and doodling. It's very exciting to see this idea formalized in an academic paper.
Yes. Oh, this one. Oh. That looks great.
Yes, you should see the poster UglyNet, playful exploration for UNet for glitch effects.
Yes, I'm sure that... Ooh. From the title, I thought that this paper would be about kernels. Unfortunately, I was mistaken. Yes. Yeah, no, I was part of that war, actually, when I was at NYU.
Paper Dreams, an interactive interface for generative visual expression.
Yes, I'm sure that the other Yann LeCun would say, my 5-year-old could have done that. My 5-year layer ConvNet could do that. That's the new thing.
It's all about training still and learning. Yeah. Oh, this is good. Styling audio reactive visuals.
Yes, you know what? That reminds me. The first time I went to NIPS,
Yeah.
it was called NIPS at the time, 2008. In Yann's lab, we were all sharing hotel rooms.
A single hotel room?
Yes, all of us, all his lab. Yes.
Well,
Yes.
that's a great choice by Yann LeCun.
Yes. Well, so anyway, times have changed.
Yeah.
I guess. Anyway.
This may be a good time to point out that the reaction of both audio and visuals to ConvNets points to their universal applicability to problems of perception and intelligence more broadly.
Oh, this one. Breaking speech recognizers to imagine lyrics.
As if something being broken means it's working in another domain. A very creative application of something being completely broken.
Yeah.
I love this. This is what art is all about.
But you know what? If you know Yann well, real music, like Bach and jazz, does not need any speech recognition. No lyrics.
Put his nose up at it.
So.
This is good. A generative approach to Korean abstract painting, dansekwa.
Do you have any joke on that?
No.
Okay.
Oh, luckily Yann LeCun does. Well, this paper claims that some images are happy and others are sad. In fact, there's an element of happiness associated with any image produced by a ConvNet. Hashtag feel to learn. Yann just loves ConvNets.
Yes, he does. Oh,
this is
tell
good.
Me that. Tell me, set the joke.
Very good. Deep reinforcement learning for 2D soft body locomotion.
What did you just say?
I said deep reinforcement learning.
Wait, this second and third word?
Reinforcement learning, Yann.
Come on. Come on.
It's the best part of the cake. Creative GANs for generating poems, lyrics, and metaphors. We can see one of the samples here. Home, home, home sweet home. Home sweet, home, 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 home. A fantastic sample from the model. Absolutely cherry-picked for sure.
They've really reduced the computational complexity on the softmax output.
Yes.
Oh.
I like to imagine that in the imagination of a GAN, most metaphors would relate world concepts to components of a convolutional neural net. Hashtag feel to learn.
Yes.
Transform the set. Memory attentive generation of guided and unguided image collages.
Ooh. For about a decade, when CPR would not publish papers on neural networks, I made collage out of rejected drafts. Now I make a collage out of diamonds while looking out of Manhattan from my penthouse balcony.
Hashtag torched. Very good. Little close to home. Little close. Neural painters, a learned differentiable constraint for generating brushstroke paintings.
Look at that, beautiful panda.
Fantastic. Figure 11 is when they chose to include the pandas in this paper.
Can we see some pandas?
Yeah, these are optimal pandas.
Yes.
Yeah, that is definitely an optimal panda.
Do we have to advance?
No, we could just watch this all day. Yeah, the next 20 minutes is just watching a panda go down a plywood slide.
It's so cute.
Yeah.
Oh.
Yann LeCun says, the optimal panda should be 1, be self-supervised. 2, play the electronic wind instrument. 3, hashtag feel to learn.
No, but it's actually true. I mean, I don't know how many people here know that Yann is playing lots of instruments. Yeah, it's true.
Yeah. Mostly hot air at this point. That was a burn on myself. I don't know what anyone is upset about.
Okay. That's beautiful.
Searching for an unstable equilibrium is experiments in training generative models without data.
I mean,
this is great. This is great. This is beautiful.
That's the best way to solve most of the controversies.
Yeah. Machine
like
learning.
Everything, like bias, everything.
There's no data.
Just, that's so pure and minimalistic.
Yeah.
Yes.
And the outputs are wonderful. Yann LeCun says,
if it is possible to learn from non-experience, then the field is in excellent position.
hashtag feel to learn.
That seems like a meta commentary. Anyway.
I love this. Immersions. How does music sound to artificial ears?
Well, I don't have any joke because that guy already actually won the demo award.
Oh, wow.
Yeah.
Okay, so no jokes allowed. He's like immune, like Survivor for the year.
Yes.
Okay. Game design using creative AI.
Yeah, because normally what happens is that sometimes in our day jobs, we like have machines playing games.
Yes. Now at this point, we've offloaded that work to the machines so they can just make games for themselves to play.
Exactly.
Yeah, and we could just sit and watch them create games and then solve games.
That's so great.
And then present the paper later.
All the cycle, end to end.
Yeah. This is arguably my favorite figure in the whole workshop. Learned interpolation for 3D generation.
Yes, this is a meta-commentary on essentially one of those things that was put in reference with that work that was...
Marcel Duchamp.
Exactly.
Yes. This is the toilet of our generation.
Yes. But hopefully that GAN also knows how to do something else, because it's not a well-known fact that Marcel Duchamp was actually also a great painter. Yeah. I'm not trying to say jokes, I'm just trying to say facts.
Yeah, we can tell. We can all tell.
Yeah, sorry, I need to... Okay.
Lucid dream, controlled temporally consistent deep dream on videos. This is if you want to control yourself through the deep dream space, you can actually take control like a lucid dream and drive yourself through this imaginative video. The end.
Machine learning-based co-creative design framework and human and GAN collaboration to create haute couture dress.
Oh, this is dangerous.
This is dangerous, yes. You can make a faux pas.
What? How so?
On walking on the catwalk? Sorry, it's... no, so basically, yeah, so perfume and haute couture, this is the kind of things that would trick Jan, because he was always very sensitive about jokes about French people. Yeah, that was the best way to fire him up.
Okay, and fashion and fragrance are French associates.
Yeah, as a cliché, yes.
Yeah. If you just acknowledge the stereotype, then it's fine.
Yes, exactly, which I did. So location conditional image generation using generative adversarial networks.
Yes, perfect. So this is the work that shows us what these architectures look like. So we don't no longer need tourism. We can just look at these pictures. It actually frees up all this world, and we can imagine great works from other societies, generations. We don't need to create anything anymore. I'm just saying, leave it up to the GANs.
Okay. Personalizing a music VAE model with user data. So that's actually a demo that you should be listening to, because of course it doesn't, you can't dance architecture and you can't draw music. You can, but anyway. Just making it up.
Text conditional lyric video generation. One of my favorite works in this entire workshop. This takes inputs of text, outputs videos that you can watch along with the lyric videos.
Yes.
The end. Oh, this is a soft spot, close to home.
Yeah,
a robot and a comedian walk into a bar and, aha! It's a good title for a paper.
So the thing is, we could have
Right?
We could have talked about Jamie Brew and about Botnik Studios and all that work. But No, it said no. Actually, you know where I heard that sentence already?
Where? Oh, on that picture of you in the New
York.
York.
It's sassy.
Okay.
That's a picture of you. It's always the joke that comes back.
Yeah. It's as if all these human headline writers were just writing the same joke over and over again.
No, so basically this is like a complete self-promotion. We literally took this opportunity to actually talk about our own work. So thank you very much, organizers.
Yeah, we're doing a show in London later tonight, which physically is impossible for any of you to attend.
Yes, but and we have many other shows. We're called Improbotics, and I think we should.
Yeah.
So neural loops.
Neural loops.
This work reminds us that the passage of time itself is a 1D convolution.
Hashtag feel the learn. Dialogue on a canvas with a machine. A human and a machine painting together on large format abstract paintings. Yeah. A beautiful dialogue to actually capture this human-machine co-creativity.
This work helps humans to expand their creative capacities. I will not comment on how I expanded my creative capacities in the 70s. Let's just call it a convolution.
Hashtag feel the learn. Yes. And now, of course, our favorite section of this talk, poster titles starting with towards.
Like everything.
Yeah. Which is the easiest way to say that there's no actual work going on in the paper. But we've thought of something cool before anybody else, so let's get into it.
Yeah, so like,
Yeah.
that's
No
all.
offense, I do have a towards paper also. No offense taken.
Punching up and down
Yeah.
at the same time. Towards a principal evaluation of likability for machine-generated art.
Seems like a hard problem. Throw towards in there and you're good.
On the topic of popularity contests, the convolutional neural network was recently named by Lyon magazine to be the #1 most popular invention in France of the late 50 years.
That's true.
Yes.
Artist in the cloud towards an autonomous artist.
Like, really? Like everything is going to be automated?
The entire process, yeah.
So
From
we-
generation to consumption.
So can we also have an audience of robots watching robot performers performing?
Yeah, everyone in here is just going to be a bot eventually at NeurIPS. And the presenters will be bots.
And then at the end, the few humans left would just be a fly on the wall just watching and
Whispering to each other.
yeah. At first, I thought Artists in the Cloud was a paper about Twitter parody accounts. Despite my disappointment, I will try to attend this poster.
Very good. And first steps towards collaborative poetry generation.
It's actually great to see like what goes in the mind of a scientist. Batman riding a dolphin up high.
That's the human's input.
Yes, that's a human's input, yes.
Yeah. I just want to clarify the peak of poetic generation. That's the human that added that part.
Yeah. Anyway.
Bourdian Lacoon says, this collaboration is a nice idea, but note that the finest poetry ever flows from the storied collaboration between the 2D convolution and the max pooling operation. Towards sustainable architecture, 3D convolutional neural networks for computational fluid dynamics, simulation, and reverse design workflow.
This kind of won the award for the longest title.
It did indeed.
Oh, I just destroyed the punchline. The length of this paper title may be daunting, but fortunately you can handle it using convolutional neural networks with mean pooling.
Hashtag feel to learn.
And yeah, so what's the moral of the story?
The moral of the story is this is very heavily inspired by convolutional neural networks.
Yes.
There's a few things you should know. 1, that they're convolutional. 2, they're neural. 3, they're networks. 4, people call them CNNs. And if you want to find any related work...
Oh yes, there is a lot of work published about
Yeah.
Yes. Yes.
So thank you so much. Please enjoy all of the poster sessions.
Yeah, I mean, we can't possibly not thank Bourdian Lequin. It's not us.
Yes.
It's not us. Honestly, this was like, we did that last night.
Yeah.
And we just kept exchanging on Twitter DM messages with Bourdian Lequin. I have no idea who it is.
Yeah.
His Gmail address is bourdian
Maybe maybe he there.
She, yes, exactly.
Yeah.
Yeah.
So
we
if
have
you're
no
in the
idea.
room, thank you so much, Bourdian Lacoon. If you're
Yes.
not, sorry for what we did to your text. If you want to find out about me and Piotr, check out improbonics.org.
This is
This is Piotr Murawski. Thank you so much, everybody.
Yes.
So thanks to our Jan Lacoons. In case it wasn't obvious, those are the real posters that we'll be presenting. Hope you come back and see the posters. And we really did have Jan on the schedule, and maybe if there's one lesson is don't cancel on our workshop next year. Okay, if you're doing an artist spotlight, the next section of this is going to be the artist spotlight. We have a few artists that are doing spotlights. I think we're going to start with Maya. And then after that, we'll do a couple more. So if you can make your way up. I'll stay right over here. Okay.
Hi, everyone. My name is Maya Petric, and I'm an artist working in immersive installation mostly, and immersive sculptures. And for this, I usually combine light, sound, and technologies such as AI, machine learning, computer vision. And I'm very interested in evoking the sublimity of nature that engages human relationship with the environment and with each other, the living beings, and creates a sense that we are part of something bigger than oneself. In this work that I will be showing you, it's unlike my typical work. It's a series of computer-generated images that are exploring how we as a world, as a community of people in this world, are viewing nature that is being affected by climate change. It is called Low Skies, and Here you're seeing two images, and both of them are trying to achieve this all-encompassing perspective on air pollution. So on your left, you're seeing air pollution through the eyes of the climate change believer, and on the right, through the eyes of the climate change skeptic. And this were done in collaboration with computer scientist Mihai Jalobenu. We were trying to create an algorithm that can search the internet and collect thousands of images on this topic, in this case, air pollution. There are many other topics, and then review all the images, analyze their salient properties, and summarize the data into one archetypal image that is impressionistically interesting as a whole, but then when you're looking into details of the image, you can find the combination of different images, creating a new narrative that I think tells a better story of the total problem than just isolated cases. And of course, these are like constructed narratives. I'm going to show you a short video that shows the process of making. So here you can see the algorithm analyzing the data and populating the images based on the color and shapes, and at the end it creates an image that is a sum of all the individual images that it's looked at. I present this in form of light boxes, but I also publish them online where you can zoom in, and it's pretty zoomable, and the things that you can see here you can zoom into further and discover details within details. This is the epitome of California wildfires that happened 2 years ago, and here you can see the effect of zooming into the image. I'm very interested in this new story that's created by combining all these individual stories and in a really fictional way. But I think this fiction can tell us more about the real truth of our reality than just the individual news. This image is showing the deforestation through the eyes of a climate change skeptic. I'm very interested also in the view that climate change skeptics have of nature, and these are kind of utopian views of deforestation. This is of a climate change believer. For the sake of time, I'm going through this fairly quickly. I believe we have the pieces outside right now, but you can also see them online. This is Arctic habitat disappearing through the eyes of a climate change skeptic. Again, I find them the most interesting once you start zooming in and discovering these weird scenarios. And this is through the eyes of a believer. This one is looking at the extreme weather events that are happening due to climate change through the eyes of the skeptic. And this one is looking at the Hurricane Maria that happened in Puerto Rico. Here you can see some of the details from the image that are showing people that were in the situations. Okay, I'm out of time. This is a tsunami, overpopulation, plastic in the water, and many more. Thank you very much.
Great. Next will be Joanne, and I'll let you introduce yourself, but I'll get your slideshow going. There you go.
Okay, thank you. So my name's Joanne Hasty, and I'm an artist based here in Vancouver. I've been a painter as long as I can remember, but for the past 2 years, I've been painting with a robotic arm. So in the next 5 minutes, I want to try to explain the development of working with an arm for the past 2 years. So one of the biggest unknowns for me is my background is mechanical engineering and painting. So could I actually program? So the first year was spent learning Python. These two paintings are the first paintings I got out of my robot. So the first one is just randomly placing brushstrokes on a page with one color. And then my 14th robot painting, I finally started trying 2 colors. So I'm more well known for cityscapes and landscapes with bright, vibrant colors. So here's a painting of Granville Island Market in Vancouver, 36 by 36 on canvas. And here's one of my robot paintings. So I wanted to explain some of the intuitions I bring from my painting by hand into the robot. So one of the things is I like bright, vibrant colors, and I don't like when they mix on the page. So when I program the robot, each time it needs a new color, it actually cleans the brush, waits a couple minutes for the paint to dry before adding more paint. I also noticed that as a painter, when I fill in a shape, I actually use parallel lines. So whenever the robot needs to fill in a shape with color, it uses parallel lines. The other thing I thought about was our arms have elbows and shoulders and wrists, so there's a pivot point. So to make the robot work look more painterly, I have it always painting curves. So here's some of my early robot work, and this is before I started adding machine learning into it and classifiers. So I took a break from working with the robot and started seeing what I could do with machine learning. One of the things I was most interested in was, could I optimize what a painting is? So my first project, I was actually collaging digital geometric shapes, and then I would use a classifier to judge whether they were good or bad based on the composition and the color combinations. I would then go back and title the painting based on the untrained classifier. So I would get names like bulletproof vest, birdhouse, envelope. Most of the time I got envelope, and that's because I believe it's because of the flat geometric shapes that I was painting. So I kept going and I kept learning. Every time I've tried to explain this slide, my talk ends up being 15 minutes. So don't hesitate to come talk to me if you want to find out about all my painting projects. But the one thing I learned experimenting with GANs is I really enjoyed using the StyleGAN. This is because it uses a paired training set. And one thing from painting for over a decade now is I have a lot of reference photos and paintings that I can then have the paired data set and train it back and forth. The other thing I learned is working in generative art, I get a lot of data. So I like to use classifiers to then help me rank what I'm doing. So fast forward to last July, I actually got those 9 paintings that you saw earlier into a gallery show. The gallery curator came and visited my studio, and she actually saw the robot painting and said, hey, bring it to the opening reception. Now, because it was all hard-coded, I didn't know if the robot could paint something good during the show. So actually, for the next 2 weeks, not only did I have to make my code more efficient to work in a gallery setting, build the stand that it now uses, I also added a classifier to the robot, so now I could train it to paint good paintings. Fortunately for that show, I was able to hide, as soon as the robot was done, I would hide the painting in the curator's office so no one actually had to see if it was good or not. But for my next 2 shows, I pitched the same idea, but I said I would hang the paintings, and over the course of the show, you would get a whole series of paintings. So now I had to dig a little bit deeper and try to train the classifier to not only create good paintings, but paintings that would hang cohesively on the wall. So you can see here I have a setup in my studio where I was trying to figure out what colors go well together when hung together on the wall. So I wanted to show a little bit about the classifier that I'm using. So here are a set of paintings on the right that are classified as good. So these are high-ranking paintings. And you can see the very first one, so that's a digital version of the painting, and it's what I see before the robot paints it. And then you can see on the other side of the screen, there's the robot painting it at a show, and then there's the final painting. So most people, when they say, well, the classifier's trained on your preferences, well, what's bad? Because art is so subjective. Well, here are the ones that are ranked the lowest. So as you can see, basically the whole page is covered with navy or gray or brown brush strokes. There's no focal point. So basically, overall, I agree with this, what the classifier is doing. So I watch this as I'm generating art. So my next project is I actually have this bigger robot. I'm really excited about using it because not only can I paint bigger paintings, but I can also manipulate the brush in space more and make even more painterly images. And that's all the time I have. Here's how to reach me. Probably the most interesting link is the last one on my Instagram account, @paintingvariables. There I have chronologically what my robot's been doing, so you can see the very first painting all the way to the latest, most recent painting. Thank you.
Great, thanks. I know it's very challenging to summarize everything in 5 minutes, so kudos to everyone for doing a good job with that. So our last slideshow, if I can remember how this works. Where is this? Oh, it's here, yes. Is Vibert, and I will let you go ahead.
Thanks.
Yeah, I can do it if you want.
Can I open that?
Let's view.
I
presenter.
want to open the link.
Oh, you want to open the link?
Yeah.
Okay.
Is that-
I do not know, but I can try to guess with you.
Chrome will be fine.
I do not. I think that's not going to work actually.
Oh.
So you have to stay in. You have to stay in this.
Okay,
section. So
got it.
So you can do view. Presenter view.
Okay.
Sorry about that.
Yeah, sorry. Hi, I'm Vibert, and I came from a background of electrical engineering, and I'm also really interested in music in general. And when I was in university, I started to exploring this intersection between this different area, and throughout all my journey through this exploring the intersection, I found that my personal goal to be making music easier for everyone to play with. Then I found that machine learning have some really interesting results in the past few years. So I started doing research about musical machine learning, but I suddenly felt that it's really hard to explain what I was doing with all the machine learning and music to my musician friends. That's quite the problem, because if I cannot really explain it to them, then how can I persuade them to use them in their musical composition, or persuade them to use it to create more interesting music result? Then I started exploring this idea of using gamification, using gamification to make the musical machine learning algorithm more understandable and fun. And I think the process of game making forced me to think about an easier approach to explain things to people who have no background knowledge about machine learning or music. Then so the first step is I create this game called Sorting. We all familiar with how VAE works, and usually VAE can create interpolation between the training data, like faces, or on this example, this game is called Sorting. The player has to figure out the original order of the interpolation between two different melodies. And you can see here this is a screenshot of the game playing. Unfortunately, I cannot show the demo here, but on the upper side of the screen, you can see on the left side is one melody, and on the right side is the different melody. And it's like a puzzle game. There's a five part of the interpolation, and I randomize it and remove it from the original interpolation and ask the player to reorganize, to reconstruct the interpolation created by a machine learning model. So it's designed as a puzzle game that you have to, as a player, you have to listen to the music and think about which interpolation is close to the left melody and which interpolation is close to the right melody. And throughout this process, you can somehow really understand how this interpolation works, even if you don't have any background knowledge about music or about machine learning. So after this, this is based on open source work by Google Magenta. They released a lot of amazing musical machine learning model on JavaScript on the web. And furthermore, there's a really interesting aspect of this work that we know that evaluating the generation result from a VAE is really hard, especially for music. There's no really solid metric for evaluating the musically meaningful of a piece of melody. And in this work, if the player, I think that there's a really interesting point that if some of the interpolation are getting the higher score from the players, that somehow means that people can, just by listening to the interpolation and reconstruct the melody interpolation, that means that the interpolation is musically meaningful to common human ears. That is really interesting. I think that by playing this game is a really interesting way to evaluate the result of interpolation by VAE. And also, I'm not trying to justify the result of the interpolation is perfect here. The user will find that some of the interpolation act really weird, and some of that is not really musically meaningful, and some of them are really hard to play with. But that's one of the purpose of this game design. It's making you learn about this model throughout whole the process of playing. And yeah. And if you want to play with this game, you can access it. Right now, it's not mobile friendly, so you might have to use it with your computer. And also, I have also developed different games. I take this further. I developed the other game called Run. That is a game that even if you don't have any knowledge about music or machine learning, you can play the game and listen through the whole song generated by a machine learning model. That is, I think there's a more accessible, if you can make machine learning model more accessible or more understandable for artists and musicians, that will help them think more about what this can do or what's the possibility of the generation out of these models. Thanks.
Great, thanks to all of our artists and the artist talks. We're going to do a little AV switch here and get started in about 1 more minute. We're plugging your computer in?
Yes.
Okay.
So we're to the presentation and if I'll look it up first, then we'll do we just lose the adapter. Is that we lost the adapter. Here we go.
Okay. I guess it's in mirrored mode.
Do you know math better than I do?
What's going on?
Is this
Oh, is that right?
Do you know what?
I think you have to drag.
Here you
Just slide it over.
Oh, where? But that's not going into.
There you go.
Oh, I see.
That's not the phone.
Oh, is that not going to do what you want?
It's
though?
not going into phone mode at that point though.
Yeah, sure.
Should we end that? Let me just end this. See if that. I don't know. Hi, thank you. Very happy to introduce Ray Nakano, who is going to, thinking a lot about getting computers to understand and imagine the way humans do, and talking to us more about neural painters and maybe optimized pandas. I'm not sure. All right, thanks.
Hi everyone, I'm Ray Nakano, and today I'll be presenting Differentiable Paintbrushes, which is about my paper, Neural Painters will learn differentiable constraint for generating brushstroke paintings. So here's a quick outline of today's talk. First, I'd like to talk quickly about the motivation for this work. I was looking for ways to get a neural network to paint, and one of the first things I looked at was this algorithm spiral. I guess the GIFs aren't playing. Hold on. Should I just, yeah.
Is it possible to not the presenter mode?
Okay, it's fine. Yeah. We can skip the presenter mode then.
There you go. If you want, let me try one more time. Just present. It's fine.
All right, so I guess it's still not playing. Okay, I guess the other GIFs are playing, so it should be fine. All right, so for Spiral, the motivation was to reconstruct images with brushstrokes from an external paint program. They used RL for this, but it required tons of compute, which I didn't really have access to. So I started looking elsewhere. I looked at world models by by Ha and Schmidhuber. It learns a world model of a non-differentiable environment via a neural network. It's used as model-based RL, and the most important thing about this is it leads to sample-efficient performance. So knowing about those two works, I had an answer to my question, how do we get neural networks to paint? My answer was to give it a differentiable paintbrush, or more accurately, learn a world model of a paint environment with a neural network. This differentiable paintbrush is what I call a neural painter, and it is the basis of every other work I'll be talking about today. So how do we actually train this neural painter? A neural painter is simply a neural net trained to simulate a real painting program. We use MyPaint, which is the same one used by Spiral. So we start off with an action vector, which is just a set of numbers that defines a brushstroke, start, end position, color, thickness, pressure. We pass it through MyPaint, and we get what we call the real brushstroke. We pass the same vector into a neural painter, and we get a generated brushstroke. So the goal of training a neural painter is to just get these two to look as much alike as possible. We have two ways of training neural painters. We have a VAE approach and a GAN approach. I'm not going to go too much into the details of this one, but you can take a look at the paper, and I'll be at the poster session later. For training neural painters, using VAE, VAEs are easy to train, but the brushstrokes end up smudged and a bit blurry. On the left, you can see the real brushstroke, and on the right, you can see the reconstructed VAE image. So to solve this kind of blurry effect, we train a GAN on brushstrokes. Now the brushstrokes are rougher and they look more realistic. Of course, it's a bit longer. It takes a bit longer to train, and it's a bit more difficult. One final thing I'd like to talk about before moving on is the concept of a neural canvas. So a neural painter maps a single action to a single brushstroke, but paintings are composed of multiple brushstrokes. So we actually work with groups of action vectors, which are then mapped by a neural painter into groups of brushstrokes that are then mapped on top of each other. This is a more detailed diagram of the process, but where we can see the group of action vectors getting mapped into the final canvas. But the most important part of this is that there's an unbroken chain of differentiable operations from the action vectors to the final canvas. That means that we can use frameworks like TensorFlow and PyTorch to keep track of all the derivatives. I'll quickly talk about the first application of neural painters, which I tried recreating Spiral, which is, of course, what started this whole thing. This is the details of Spiral. We use some kind of an adversarial training approach, and I guess it just don't show up either. Oh well. But yeah, the main point is that we tried celib A, MNIST, and KMNIST images, and for the and they were sample efficient. I was able to train it without DeepMind level resources, and I was able to train it using only a single free Google Collaborator GPU. Another way to think about the neural painter is as a differentiable image parameterization. A differentiable image parameterization is work from Mordvintsev et al., where we map a group of parameters using differentiable transforms into an RGB image. This allows us to optimize the image with respect to the original parameters via backpropagation. So where have you seen this pattern before? A neural painter is exactly a differentiable image parameterization, where your group of numbers are the group of action vectors. The neural painter is a completely differentiable transform, and you get the final canvas as the output. Including a loss function into this, you'll be able to backprop directly into the group of action vectors and update with any way you want using Atom. So in essence, you're trying to optimize brushstrokes directly using backpropagation to optimize whatever loss function you want. So the main idea of this is that most artworks today generate pixels directly, but painters paint using brushstrokes, not pixels. So in essence, instead of generating each pixel directly, we generate the brushstrokes directly. So looking into the first application, so the question now becomes, what loss functions are interesting to use? The first loss function I'll try to use is maximizing ImageNet classes. So we've seen the work by Tom White in synthetic abstractions and feature visualization by Ola et al., where a pre-trained network is actually used to calculate the loss function. So given a network trained on ImageNet, we iteratively adjust an image in order to maximize the output probability of a particular class. Starting from the action space of brushstrokes, we pass it through a neural painter, we get the final image. We pass that final image into a pre-trained ConvNet and try to maximize an ImageNet probability. Following on from work by Tom White, we optimize multiple classifiers at the same time. So trying to convince multiple classifiers that something is, for example, a starfish gives us more robust results. A fun way to interpret this is if we're optimizing the panda category, for example, the output can be interpreted as the answer to the question, given a paintbrush, how would a pre-trained ImageNet classifier paint the optimal panda? And we saw this earlier, but here are a bunch of optimal pandas. I actually have like a printout of the optimal panda here. It's really small, but it'll be at the poster session if you want to take a closer look. A few more optimal classes. We have polar bears, bees, and lemons. Okay, this animation works. So we see here the actual optimization process. Each frame is a gradient step, trying to optimize the optimal panda, optimal monarch butterfly, and the optimal violin. Last, I'd like to show the intrinsic style transfer part of the paper. In regular neural style transfer, we optimize an image to minimize a content loss and a style loss. But in intrinsic style transfer, we throw away the style loss, and the content objective completely preserves only the higher level structure in the content image, allowing the parameterization, the neural painter itself, to fill out the details. So the artistic medium itself serves as the intrinsic style. Okay, the animated GIFs work. We can see animations of the, what is this, Science World, the Louvre, and the Sydney Opera House. So the reason it looks kind of like a printer is because I'm stitching together multiple 64 by 64 pixel canvases. The neural painter is only trained to generate 64 pixel canvases, because that's how much my GPU can take. But we're able to stitch them together to get any resolution images we want. So, okay, this works too. We can use it with like panorama-like images for Big Ben and the Statue of Liberty. Finally, I'd like to say that we can actually intentionally limit our brushstrokes. So for example, on the left side, we can see that we can constrain the brushstrokes to use only grayscale strokes, which makes it look as if it's drawing something using a pencil. And on the right side, using different layers of a pre-trained neural network can lead to really radical differences. This is using the same network, but optimizing a different layer. In layer 3A, it's lower layer, so it's closer to the pixel level loss, meaning it tries to preserve the colors, while just going one level lower, one level higher, I mean layer 3B, it can imagine its own colors, and yeah. As the last slide of this talk, I'd like to share something I've been working on for the past few weeks. I just implemented a new PyTorch library for neural painters. It has pre-trained neural painters, so VAE and GAN neural painters. It has easy-to-use modules for neural canvases that allow you to that do all the color blending and canvas stitching automatically. It has a visualization utility for creating all the animations I showed in this talk. And most importantly, there are example collaborator notebooks, so you can build on from those. Yeah.
Thanks. In the interest of time, we're going to skip questions, but all the presenters will be at the poster session later, and feel free to come with questions at that point. So great. So next we'll be hearing about creating collages of images. Let me find. Do you want to have the PDF up?
Oh, yeah, just the PDF.
Okay, great.
It's simple, no animations.
Okay.
And at some point, at the 7th minute or so, I would show a video. I think it must be preloaded. Is
The video's there?
available? Ah, yeah.
Yeah.
All right. So can then, if I need to, I can ask you like what to click
How
after
to find
7
through that?
minutes.
Excellent.
All right.
Okay, great.
I'm not a Mac user usually.
Okay.
All right.
Just trying to. There we go. I'll bring this over instead. Okay, so thank you, and welcoming Nikolay Jeshchev to present.
Hi there. So it's a great pleasure to. All right. Thank you. So it's a great pleasure to be here for the third time at the Creativity and AI workshop. It's really inspiring event. And I will talk today about my work. I'm Nikolay, and with my collaborators, Urs, Gökhan, and Rowan from Zalando Research in Berlin, Germany. And I'll present our work, Memory Attentive Generation of Image Collages. And this image would kind of give you the high-level idea what's going on here. Our method can get as an input a set of images. We call them the image styles. It's a set, can be a random number of them and so. And our method, aptly abbreviated MAGIC, can learn how to combine spatially coherent segments from this image. First to combine them in a collage and then refine them a bit better and change a bit the shading and airbrush it to be even more convincing to a discriminator. So this would be a form of amortized collaging. In just a single forward pass, our network can get this set of images and create a plausible output collage. And as some background, I'm not an artist, I'm a machine learning researcher. My motivation for this work was actually to create a new fancy GAN architecture to beat the state of the art. It didn't work out as well yet, but at least it allowed me to create some nice images and to do some nice art experiments using this architecture. Okay, but first of all, what do I mean when I say a collage? So the collage is a really old art form. It has a long history, and it's basically, at its core, a very intuitive art form. You can just start with a set of images, decide what to copy and paste from them, paste them into the canvas, and get your output collage. But this form is also very versatile, like what to copy, where to paste, should it be smooth or with hard borders, should it be photorealistic or surreal, we can do a lot with it. So here's some example. This is from the 18th century, Mary Delaney in England. She would cut diligently hundreds of pieces of paper and paste them into some flowers, and her flowers are so amazing you would think they were painted with a brush or even photographed. Of course, there was no photography at this time, but this is an example of an amazing photorealistic collage. Coming more recently to more modern times, people like to play with surreal and shocking art. Here, Annegret Soltau, who would cut pieces of human faces and bodies and stitch them into some composite humans. It's not photorealistic, but it's also quite provoking. It evokes a strong emotion into the human observer. Okay, here I would give a very, very brief overview of some digital collage tools. It's incomplete, but it would give you some idea about what are the challenges and the forms in digital collage tools. So first, the Jigsaw image mosaics. It's a mosaic tool, but also somehow fit the collage definition. You start with many, many small image styles, and then you paste them into some form, into some content, which guides the mosaic collage. And it's quite cool on its own, but has some drawbacks. You really need to have these many, many small images. It's also very expensive to optimize just for a certain mosaic. And it's not deep learning, so we can do other than that. Second, non-parametric texture transfer by Efrus and Freeman. It's a classical work in computer vision. It's quite awesome when you want to sample textures or to do texture transfer, but it also has some drawbacks. It's really slow. Even for a small image, 200-something pixels or so, it would take a few minutes. It has some very expensive nearest neighbor search routines, and it's also a bit limited that you only use the pixels which are already in a training set. You cannot go away from them. As third example, I wanted to mention neural style transfer. Yeah, like everybody here is aware of it, I'm sure. It's not actually a collage tool, but I want to mention it to kind of emphasize the difference, why it's not a collage tool. With the neural style transfer, you kind of pick up things like the hue, the brush form, the edges, kind of the things which make up the style of an image, but it's not strictly a collage because you're not copying spatially recognizable segments. And actually, my inspiration was, let's do a collage, but which takes maybe the good aspects of neural style transfer, like that it's smooth and you have this nice blending between images. Okay, and in the second half of my talk, I would go into detail about our new generative collage tool, Magic. And I think it's a new tool. It is very fast to train, very fast to do inference. It addresses some of the shortcomings of previous collage tools. And it's also quite fun to use on its own. And since we don't have hard quantitative measures, is it better, is it not better? I think it's just a qualitatively new way to make collages, and it's quite fun to use. So first of all, this is like the only deep learning-like slide in my talk, like a high-level overview, what's new about Magic. It's basically a GAN where the generator architecture has some key new features. So basically, it should take as input a whole set, a set of variable cardinality of input style images and transform them in a single forward pass into an output collage. It should do it just in a single forward pass, no search, no optimization. And it would be trained end-to-end as a GAN. And we call this a hybrid parametric, non-parametric generator because it can flexibly decide, do I copy and paste something from the memory templates? Do I copy and paste something from the existing images? Or do I use my convolutional layers and filters to create some new content? So kind of this architecture is flexible and it can decide fully differentiably where to copy and where to paint new. And yeah, I will speak more at my posters about the architecture. I think it's quite cool, but the key ingredient here is a set transformer layer, which allows it to reason about these whole sets of memory images and to think about their interactions and to kind of see which segments would fit where exactly and give a nice result to fool the discriminator. And with this, when it comes to using this tool at inference time, it's a very versatile tool which supports many, many options. You can do a guided or unguided collage. You can use many, many small images. You can use just a single big style image and kind of transform it. You can stitch very large posters. You can do even video texture transfer. It's a very versatile tool. And in the remaining few minutes of my talk, I will show you a few examples. Okay, so first of all, I think this would be the most canonic use of the Magic tool. Some very large-scale content-guided collage posters. So this thing here has like 2,000-something pixels resolution. We will take a style image, The Triumph of Death, an amazing painting by Bruegel from the 16th century, and as guided content image, the eye of M.C. Escher, another cool thing of art. And with the Magic, we can train it just for this style image and this content image, and it would be able to produce a large collage which faithfully keeps details of the style image, but also is able to blend them smoothly into one another. And here's some more detail how this magic happened. First of all, training is patch-based, which is very efficient. So at the end, it only takes like, for this example, only took like 15 minutes to train the model and then to infer the collage. We would sample patches from the content and the style image, small patches of fixed size. And then as the training progresses with GAN loss, like end-to-end adversarial learning, our method would learn to recombine randomly sampled patches from the style to infer a blending mask and to recombine them so that you paint as good as possible the content patch. And then at inference time, things get more interesting. We have like the style image, which is, let's say here, very big, like 3,000 times 3,000 pixels, and the content image, which is a bit smaller, 2,000 something pixels. First, we would create many templates from the style image. We would randomly offset them, shift them, or deform them in some way. So we would get a big, I think, around 50 elements in this set of memory templates. Oops. Then Magic would run its convolutional and set transformer layers, and it would predict a blending mask in order to paint the eye. And then finally, this blending mask would be used to create a collage and optionally airbrush it into an even more photorealistic collage. Second example is actually we can do video texture transfer with this tool. We can use a whole video texture, and because we have a fully differentiable smooth forward mapping, at inference time we can just input subsequent frames of the video texture and create the video collage. Maybe I can open here the video. I hope it works. I should, okay, it works, and just need to move it. Maybe you can help me with the Apple.
Sure.
Yeah, I'm not an artist. I don't use an Apple, but Ubuntu-based system. Okay. And then you can start it from the beginning. Yeah, it would be awesome. All right, thank you. Do we see it? Okay, so, okay, then this is good enough, yes. Okay, so we start with video texture from the dynamic texture dataset and the content. Then we train it on patches from the frames of the video texture and the content image so that it learns to paint faithfully these patches. So far, it's identical as in the poster case, just patches from the content and style image. And then the interesting things happen at inference time. Then we can kind of create the shifted memory templates to be shifted not only in space, but in time. And then you can do a video texture transfer using our tool, which uses that we are doing non-parametric amortized transfer. In just a single forward pass, you can predict the output collage. And this is very suitable when you want to create a video collage using these video textures. And here's some more insights into what happens inside. At every single frame, our method predicts which pixels, which segments to copy from which frame in time. And it kind of does it in this way in order to fool the discriminator to be always convincing with respect to the water texture, but also convincing with respect to the time dynamics. Okay. And then I go back to my talk, full screen, to go full screen here. Sorry. Okay, awesome. Okay, so yes, we are almost there. Last but not least, I wanted to show you something else which is quite fun. One can actually do some caricatures, making a facial mix-up. First, we train our magic model on the CELEPEY dataset to make human collages. And afterwards, once it's trained, we can have some fun with it and do out-of-sample inference. We start here with the picture of some famous world leaders, and then we can predict some collages which show kind of some mixes. What blend do you want between these two world leaders? Pick up yours. So yeah, I selected this already more than a month ago. I didn't guess that the timing would be so opportune with the British elections. But yeah, and this is all. Thanks a lot for your time. Looking forward to speak to you at our poster, where I can speak more to you about architecture or give up some prints of our artworks. And yeah, as a one-sentence summary of what I showed you, this is a new hybrid GAN generator architecture which can flexibly decide where to copy and paste and where to paint directly new pixels. Thanks a lot.
Thank you. Thanks so much.
just switch to mirror. Because we don't, do they need, unless they need these.
Do you want the speaker notes there?
Yes.
Yeah.
Okay.
Can you, so then it'll display if I play here. Good. Okay. And next, Guillermo Bernal and Lily Zhu talking to us about an interactive art interface.
Good morning, everyone. My name is Guillermo Bernal, and this is my co-presenter, Lily Zhao. This work was done in collaboration with our other collaborator, Harpriya Mita, and our advisor, Patty Mays. So why did we do this project, Paper Dreams, which I forgot to introduce? But I'll give you now an insight on that. I'm a PhD student at the MIT Media Lab, and I'm part of the group, the Fluid Interfaces group. And our group looks into the idea of cognitive augmentation, and that can come from the ways of being like memory, could be learning, creativity, and well-being. So we now are developing all these amazing tools as we're seeing them around, and there's a population that actually needs a lot of these tools to feel empowered and begin to engage with a lot of these tools. So I think it's important also to spend a lot of time on developing the work that can engage with them and that they can begin to use them and feel empowered, and not just a tool to translate, but they are actually learning and actually beginning to embody a lot of this knowledge that goes into creating. And I think here everyone resonates, that's why you guys are here. But I think it's not so obvious outside of a lot of these walls. So we're targeting people that are in like elderly homes, these type of tools that can help for storytelling to cope with age, as well with parents and children that are actually growing up with a lot of these AI agents and a lot of content that are just consuming, so now they can begin to develop. So what we've done is this application called Paper Dreams, and in order to explore these topics, we built a web application, an interactive back and forth between the human artist and our system, incorporating customized machine learning models and representations to assist the user in visual expression. As you can see in the demonstration here, the result of the tool is that allows the user to quickly storyboard and generate new ideas. So how do we do this? What you see here right now is a high level of our system, and also this presentation will break down a lot of these components. So the first thing that we need is to get some insight into the user. We do this via either speech to text, text input by typing, or sketches. Now that we have an insight from the user, we use a lot of these conditional GANs to begin to texturize, or some semantics from NLP to begin to bring some other related objects. We have developed this thing called the Serendipity Wheel that we will go more in depth that can change a lot of these modalities. And we quickly introduce some of the user studies that we've done, and we'll expand that during the poster session. So as you can see here, here's one of our users using the Paper Dream application. Initially, the application has no prior knowledge on what's happening. Only until the user actually requests for some assistance, the system begins to provide some related objects on the right, and then begins to provide also some sketches that then can later be used. So how do we do the sketch recognition? I think if you've done sketch recognition, you know there are currently like two big data sets. One is kind of old now, the TU Berlin, but it has a lot of rich context, a lot of features, but are very small. And the other one is Quick Draw, where there's a large data set, but a lot of the features are not quite as developed, just because it was done in such a quick form. The information is there, but the details are missing. So we decided to start with the TU Berlin and then go with the Sketchy from Georgia Tech that they actually expanded that TU Berlin, but still not enough to do a lot of the CNN work that we are aware around here. So we extended what we call Sketchy++. We did some data augmentation to bring that data set up to 300,000 images in order to be able to train with a lot of our systems. So this is the architecture that we're following. We are using a convolution neural network that has a lot of architecture and learning parameters that are choices specific for addressing the iconic and abstract nature of sketches. Our specific architecture is as follows. We use a 5 convolutional network, convolution layers. each with a rectifying unit, with the first, second, and fifth layer followed by a max pooling. The first size, the filter size of the sixth convolutional layer is a 7 by 7, which is the same as the output from the previous pooling layer. Thus, is precisely fully connected layer. The two more connected layers are appended, and a dropout regularization is appended to the first two fully connected layers. This final layer has a 125 output unit corresponding to the 125 categories that we have in our data set, upon which we place the softmax loss. Another important thing of this is the filter size that is a large filter size as opposed with a small filter size that you see in this image recognition. Since with sketches you don't have a lot of this texture, you're better off doing a larger image.
So once the sketch recognition model has returned an identification label from within our available classes, we use this label to associate an appropriate texturizing model and pull possible inspirations from the associated concepts, which you can see here on the right. The user can then click on any of the related terms, pull from a series of images from our database, and add any image from that series to the canvas by drawing a circle in the size and location where they want it to be. So thus allowing the user to populate the canvas with pre-drawn images, their own sketches, or a colorful combination of both. So our conditional GAN follows the architecture presented by Wang et al., where the course-defined generator consists of two components. G1 is the global generator. It has three components: the front end, there's some residual blocks, and a back end, similar to standard CNN. So for the generator, we first downsample the input image. Then this downsampled image will be put into a series of residual blocks to generate the low-resolution output. G1 takes a resolution that is 1/4 the resolution, and G2, the local refiner, takes input and produces output of the desired size. Secondly, the last feature of the layer of the low-resolution output will be added to the high-resolution features and go through another series of residual blocks to output the final image. For the discriminators, we first build image pyramids for both the real and synthesized images. Then different layers in the pyramid will be fed into different discriminators to determine whether the image is real or fake. This ensures the generated image looks real both locally and globally. Finally, we also modify the objective function. Previously, we wanted to only fold the discriminator and make it output real at the last layer. What we did is we also ran the discriminator on the real image and tried to match the intermediate feature representation of both pyramids. This can be considered a learnable perceptual loss. So to summarize, these three modifications helped us generalize to high-resolution outputs. So currently, the web application supports 125 distinct classes of sketches, same as our sketch recognition. It would be impractical to train a single model for every single individual class. Therefore, we group the classes into 15 distinct models, each encompassing a relevant subset of the classes. So for example, butterfly, hedgehog, and cat are all processed by the animal model, while other examples of other models include food, landscapes, and plants. So as you can see in the video, the sketch recognition and the texturization model provide a seamless, real-time adaptive experience for the user, where there's a constant stream of visual feedback for both the user and the system. In addition to these two graphic modalities, we provide a serendipity wheel that allows the user to discover related new concepts for their sketch. By clicking on different sections of the wheel, the user can request inspirations that are closely related to their sketch or relatively unrelated and start creating a narrative in their work. So through natural language processing, NLP, we can generate and visualize the relationship between many of our concepts. Using the model SensiTiVec, we calculate the numerical cosine similarity between different concepts, which is a commonly used measure of how closely related two terms are. After generating these similarity values, which you can see above, we can see how some of the terms are more similar, like cat and dog, and some are relatively unsimilar, like cat and rocket.
Okay, so we have begun to do some user studies with our application, and see how effectively actually a lot of these different features are translating to the user. We're asking questions to understand like the prior of the user, like do they consider themselves the creative type? Have they engaged in creative activities in the past? And from that, we begin to create some sort of model on like their own behavior and their own perception on the art. We also want to know how do they feel after the creation of the whatever they had to create during the task. In this case, we're doing like storytelling. Does the art actually feels like it belongs to them, or it was just generated by the machine? And some of the results that we're seeing positive, and comparing it to an application like Adobe Sketch on the iPad, and seeing like, does it feel the same? Do you have the same authorship or not? We're seeing positive result on feeling the authorship. We're seeing a lot of very positive results as well as seeing like the diverging of the story, meaning did the actual features of the story help you move forward, move in a different direction that you were not actually perceived or started with? So these are just a few quotes that we got from the participants, and I'll let you read it, as well as how like the colors can become part of like the influencing the perception and the mood of the story. We can go in depth in our poster section. I'll be happy to share more on details. And just to finalize, these are some creations that people have gone and explored with these models, not as what it was intended, but with their own internalization and understanding that this is just a medium. Thank you.
Great. And happy to introduce Junior Rojas to talk to us about using DeepRL to look at 2D soft body locomotion.
All right. Can you hear me in the back? Yep. Okay. So I'm Junior. I'm a PhD student at the University of Utah. And I'm going to present our work on deep reinforcement learning for 2D soft body locomotion. And this is joint work with Stelian Karas and Ladislav Kavan. So first, let me give you some context about computer animation, specifically character animation, where it's very common to define motions using angles and rotation. And this is also very common in robotics and many other areas that try to model physically realistic autonomous agents. But in particular, in character animation, we're interested in animating bodies with complex shapes. So if you want to animate something like an arm, for instance, you might have a mesh that looks like this. And the way this is handled in traditional animation is by a process called skinning, which basically converts bone transformations into mesh deformation. And the problem with this is it relies on geometric approximations, so sometimes it doesn't look very physically realistic. And this model also assumes that motion is originated by operating on joint angles. But in reality, motion is originated from muscle control. So actually, there's a very complex, there are very complex interactions between different types of tissue to achieve joint rotation, which is just a side effect of muscle contraction. So in this work, we go to the other extreme, and we simulate everything with physics. And we use completely deformable meshes with no rigid components. And one advantage of starting with a mesh is that we can already create physically realistic motions by running physical simulations. So we can do something like this, for instance, where we have a triangle mesh, and this is being simulated with a finite element method using a Neo-Hookean elasticity model. And for numerical integration, we're using the variational formulation of backward Euler, which is a very popular method in computer animation because it's very stable for large time steps. And so to go from this to character animation, we introduce an actuation mechanism inspired by muscles, where we essentially have these pink springs that are controllable. We can control their rest length. And by changing their rest lengths over time, we can get these types of motions. And now this is where reinforcement learning comes in, because in practice, we want to achieve different types of motion by different sequences of actions. So this is, for instance, something we can get by optimizing actions for horizontal locomotion using reinforcement learning. And again, this is all entirely driven by physics and muscle control. And so the way this works is that we have a neural network that is mapping this kind of observation into muscle control signals. So in a sense, this character is blind, but it has some kind of proprioception, because even if you close your eyes and you kind of move your hands, you can still feel your own, the state of your own body at any given time. So that's essentially what we have here. We're mapping these proprioceptive signals to muscle control signals. And so here's another character. And it can also control its muscles and relax them using the same mechanism. And we can do the same thing. We can just do reinforcement learning to optimize actions to achieve horizontal locomotion. Yeah, and this works just like before. We have, again, a neural network that is mapping this observation space to actions. And something important to note here is we don't have any reference motions. This is just, I mean, this coordinated muscle control just emerges as an optimal solution to achieve horizontal displacement. And another interesting thing is that at first, I thought that I would have to use explicitly periodic functions to achieve these periodic behaviors, like cosines or sines. Or recurrent neural networks. But actually, this is just running a feed-forward neural network, and it works just fine. And so, because we can run these controllers from arbitrary simulation states, we can run experiments like this, where we can add perturbations and see what happens. And actually, it can recover after some time and go back to the stable locomotion pattern. And so we can, of course, also change the reward function. So for instance, we can train this same agent with a different reward function to train it to jump. And something interesting here is, as you can see, the controller doesn't really know the distance to the floor. There's no explicit input with the distance to the floor. But I mean, by looking at the observation space, you can kind of see why it's still possible to learn where to jump to achieve this motion. And again, this is also just running a feed-forward network. And so, because we can run the controller from arbitrary simulation states, we can also switch between policies at runtime. So we can combine horizontal locomotion with jumping at any given time. And all transitions are kind of automatically handled by physics, because even if you want to do a very abrupt motion, you still have to go through the physical simulator. So you still need to kind of go against inertia and all these physical effects. So you're not going to get an abrupt motion when you transition from one controller to another. All right, so now I'm gonna give you some more details about the training process. I'm just gonna go quickly over it. So we have an interaction loop where we have these observations, and those are passed through a neural network that outputs actions, and those actions are sent to a physical simulator, which produces a new state, and this new state is used again as a new observation for the policy. And this is very common in reinforcement learning. So we have the action as a function of the policy, but actually we're using stochastic policies. So the action is actually a random variable whose distribution is conditioned on the observation. And for training, we run rollouts. So you can imagine running this training loop for H time steps. And you can also run several of these rollouts. So we collect a bunch of these rollouts for H time steps. And every time, even if you use the same initial state, you're going to get different results because the action is actually a random variable. So we have M rollouts and H time steps of the simulation, and that basically gives us training data to optimize the policy. So basically, we have data in the form of actions, observations, and rewards. And again, like I said before, we don't really have any reference motion data. This is just, we just have a simple reward function like horizontal displacement or jumping. And basically, we're using an adaptation of proximal policy optimization. If you're familiar with this method, these formulas probably look familiar to you. The only difference is that we're using, instead of learning a value function for the baseline, we just use the average score baseline for simplicity. So we only need to learn a policy network, and we don't really learn a value function. And it still works. And so if every iteration you run a few gradient descent or atom iterations on this loss function L, you get a new policy. Hopefully, it's going to be improved. And that's how we get these results, basically running this optimization process for many iterations. And that's it. Thanks.
That's fine. Yeah, it should be the first two on there. Joseph.
Okay. Is it not the rest? Oh, there. Yeah, this will just be. Okay. Great. And next we'll be hearing from Joseph Musil talking to us about applying convolutional networks to architecture.
Hello, everyone. I'm going to talk about application machine in architecture. Apparently, I'm also the winner of the longest title. So thank you for that. It's always good to get awards. So I work in a large architectural office in London, Foster & Partners. This building is one of our highlights. It's now a bit old, but you can still recognize it on the skyline in London. And I'm showing it because this building has been influenced by wind flow on the outside and on the inside as well. So on the outside, the shape basically influences the public space inside. You can code it. So this is a simulation, and you can see with the shape, you can control if a wind flow is faster or slower. So in the left image, the red simply means just by the shape, the wind gets faster, and the blue arrow means the wind gets slower. So you can do this to help people be inside public spaces because you will not get the right amount of wind outside. On the inside, you can play with the idea of natural ventilation, which is a big topic today because of the sustainability and minimizing energy consumption. So you want to basically get the airflow going through the whole building without energy. The good thing is we know there are certain values for airflow that are suitable for specific activity. So if you want to design a public space for sitting, let's say a coffee place, you need to get it within those values. If you want to have a park for walking, running, you go a bit higher. Now, interestingly, simulation can provide even better results than physical tests. The reason is if you do a physical test, which is called like wind tunnel, where you make actual physical tests, your limitation is because it's a physical model, your limitation is the model. So you generally end up having a smaller model than if you do a CFD, which is the convolutional dynamics, which is the full simulation of wind analysis. Now, so this is a traditional, this is a state-of-the-art workflow in our office. You do your simulation, you get a report, and then you try to use the report to influence the design. Now, there are two major issues. One is the time. This might take anywhere between 1 to 3 weeks based on the complexity of the building. And if you're talking about concept, this is just too slow, because in concept, your design changes literally every day. So we're looking for something faster than that. And then problem number 2 is even if you have a perfect report, there is still no easy way to influence the design, because the relationship between the buildings and the wind flow is a bit nonlinear. So what we're proposing and looking at is creating some sort of interactive fast design cycle. And we're using convolutional neural networks to do that. So there are 2 neural networks. One is taking care of fast prediction of the fluid dynamics, which I call forward direction. And then there is a second neural network which simply has the input and output swapped. So you start designing your wind flow, and it predicts where to put buildings to achieve such a wind flow. This is the same cycle shown in a graphic way. So the top row is the forward direction. As an input, you give it your meshes. Well, we are working in a voxelized space, so it's voxelized meshes of the buildings. The mid column is the ground truth. There's the CFD prediction, and at the right column, you see our prediction from the CNN. Now, you take the simulation, you put a threshold on it. The reason for that is because if you want to work directly on the wind effect, you can't really draw the full simulation, because it would be too complicated, and also it would actually include the information about the buildings. So I put a threshold on it, which leaves me with 2 areas. One is area with a wind flow slower than specific value, and the rest is areas with wind flow higher than specific value. And then again, on the bottom row, the middle column is the ground truth, and the right column is the prediction. So to achieve that, we had to build some a training set. That means I generated around 6,000 randomly generated buildings that was then fully simulated using CFD. That took maybe between 3 or 4 weeks. And then we used 90% training, 10% validation, and eventually it was all integrated in CAD software. CAD is like a computer-aided design software. That's the standard tool used when you're doing buildings. To give the data set more realism, I was using statistics both in plan, like dimensions in plan and heights from actual cities to have a data that is more valuable. The architecture of the CNN is in both cases as a unit with residual blocks. The only difference is for the forward direction, we use 3 output channels because we want the direction, but that's X, Y, Z values of the wind. And in the reverse direction, it's just one channel, which is voxelized based on saying 1 means there is a building, 0 means there isn't a building. Some more parameters, interestingly, because it's a fully convolutional network, we can train it on a small domain, then we can then predict. So it was trained on 256 by 128 meters, but the prediction you're going to see later are on a double domain. That, of course, because it's a large domain, there is a bigger chance of an error. But because generally it's predicting spaces with lots of buildings, we don't expect like a large error. It would probably be a large error if you try to predict open space, but that's not our case. Some more parameters we're using. I'm going to talk about cost function at the end. At the moment, we're just using simple mean squared error, but there are some more development already happening on replacing this. This is one sample of prediction. Interestingly, it's doing better job in higher values, which works well for us because we do care more about the higher values, which is the unwanted wind speed. This is just a few examples for you to see what the training data set looks like. Left column is a plan and section of few buildings. Middle column is the ground truth, and the right column is the first step of the prediction in the forward direction. This is in the reverse direction, so you start with the threshold valued prediction, and you predict position of buildings, volumes of buildings. So this is the workflow we end up with, and the interesting thing is you can start anywhere on this circle of workflow. The suggested workflow is that you still start with your sketch of a building, then you go use the first CNN to predict the wind flow, then you use the wind flow to modify the wind effect you work on, and then that predicts again the building. So you can continue until you are happy with the result. So eventually it was, is it playing? Okay, I'll see playing here, I'll see playing. So it was then implemented in Architect's software. So you can interactively draw your buildings, and you have immediate feedback. So you're going from days to almost like close to, this is still sped up, but it's close to real-time feedback. It's working in 3D, so you have access to the prediction in all directions. And then, so this is the moment when I'm putting threshold on the CFD, so on the wind flow, which leaves me basically with a point cloud representing the areas with, in this case, slow wind. So that's the areas I actually care about, and that's the areas I want to design. And as I'm changing it, because it's a point cloud, I can use any of my standard tool to manipulate point clouds. It gives me a prediction of where to put some buildings to achieve such a wind effect. Then I can take it, I can modify it again, and I can continue the workflow. I can verify that the prediction was working, get some CFD prediction, and so. Now a little bit talking about what's our next steps. If anyone is interested in any of those topics, please talk to me after at the end in the poster session. So we see like a major improvement would be going into mesh-based or graph-based neural networks, and then we're also looking into some sort of physics-based or potentially even GAN to replace the cost function. And this is like even bigger picture what we're looking at. Because as architects we deliver buildings, but what we deliver to users is all these effects, like you perceive spaces as by the light levels, by the sound levels, by the noise levels, by the wind flow or airflow inside. So we would like to work directly on those rather than just checking that is within certain limits. So, and all those simulations, what we have to do, they generally take lots of time, so we need to speed them up, and we also like to swap the direction, the way you design it. Thank you.
Thank you. And then for our last presentation before the break, I'd like to introduce Jun Sata, who's going to talk to us about using GANs to change the world of haute couture.
Thank you. My name is Jun Sata from Tokyo. My laboratory is actually studying deep learning on medicine, but somehow we had a chance to collaborate with one of the top wedding dress designer in Tokyo. So the initial idea was quite simple. So we use a GAN to learn her style from her past work, then give some new idea to the designer. Then the designer realize a dress. Okay. So this was the output from the GAN. Then the designer made these dresses from that image, or like this. But actually, she told us that she didn't excited enough from that output. Because here is a quite important thing. If human beings are more creative, the total number of the work that you can create in he or she lifetime is quite limited. So the AI cannot imitate that. Okay? So that's the point. So this is the bottleneck point on this project. So we came up with the idea to infuse some motif from the nature without telling GAN whether that this is her dress or, for example, spiral shells. Okay, so it's unlabeled. Okay. But that worked. So from this strategy, the output from GAN is more kind of not the random, but more creative. So the designer got excited and she made this dress or these dresses. Okay. So today I'm gonna present the final output by two ways. I'm gonna show some footage from our last show. Then we bring several dresses from Tokyo to this conference. So we're gonna present at the poster session 2. Okay. So is the music on? I think it's not connected. Yes. Oh, maybe. Let me just say, yeah, okay. Let's try this. that's it. Thank you, and see you at the poster session number 2.
So I think that was the last presentation for this. We're doing a lunch break. When we come back, we'll be doing the first poster session. If you're in the first poster session, I would recommend maybe you stick around and go ahead and put your poster up. But in either case, that will be starting after lunch at 1:30.